Hello guys, today we're going to learn how to use VIVADO HLS to generate the interfaces to the microblaze and the Zynq platform. We're going to split these videos in probably 3 or 4 videos where we're going to learn how to create IP cores that have the AXI Lite slave interface, the AXI stream, and the VRAM kind of interface. We're going to learn step by step. I'm going to choose one simple problem. The idea is not to have a complex problem, is to have a simple one, and you're going to be able to learn how to create different interfaces to your microprocessor. Okay guys? So let's switch to the board where I'm going to explain a little bit more about the theory on what you're going to learn today. And following the same set of videos, we're going to, in the end, switch to the lab and show how to do it in the VIVADO HLS. Okay? Hope you guys enjoy it, and let's go. Using VIVADO HLS to create interfaces. Okay? We're going to learn basically these 3 types of interfaces. Actually, VIVADO HLS can create a 4th one, but I don't know yet how to use them. But let's stick with what I know. So, we are going to learn how to create IP cores which have the AXI Lite slave interface, the AXI stream interface, and the VRAM. Okay? When you should use one or the other. This is the most important. The AXI Lite slave interface is really good for IP cores that does not need a stream of data. I mean, you don't need to you don't need to send, for instance, images or large arrays of data. So in those cases, the AXI Lite is a good candidate. For instance, you're going to do an IP core that do read solemn, or something that's really small. You send a small amount of data and receive a small amount of data. One important topic is that this guy here does not allow streaming of data, does not allow data bursts. Okay, the AXI stream, in other hand, accept. So use this guy, for instance, if you're going to do image processing stuff. Okay, the VRAM is going to create an interface, a memory interface to a block RAM inside your FPGA. So basically, if you have your IP core to push some data to the internal memory of the FPGA, and you want your microcontroller, or being the microblaze or the PS part of the Zynq, to access this data, you can use the VRAM. It's quite fast and reliable as well. Okay? In this video, I'm going to teach first how to create an IP core which has the AXI Lite slave interface. Okay? How you connect this guy. For instance, this guy is an IP core which has an AXI Lite slave interface for the parameters and the results. Okay? How you connect them, for instance, with the Zynq. You can configure the Zynq to have the general purpose master port enabled. Okay? That this guy is going to control your IP core through an interconnect, which is going to be able to control more than one IP core if needed. So normally when you do this connection, VIVADO will automatically put the interconnect in between. So you don't need to care about that. Okay? So let's stick with this sample now. I'm going to switch to the lab to show how to do this, and let's see what we can learn with this.
Okay guys, before we start our lab, I'll just explain a little bit what will be the problem that we are going to generate an IP core. Okay, basically we want to create an accelerator to calculate the force between 2 bodies. Okay, this is the simple gravity formula. Okay, here I'm just creating in Matlab a script that is going to be, a function in Matlab that is going to be used to create our reference. Okay, and basically what we're going to do, we're going to create a vector, okay, of tests. Okay, and then we're going to call our function by fixing the first mass to 10 and the second mass to 20. Okay, simple as that. A reference called force gold ref is created. Okay, so basically we just want to copy this. Okay, then we're going just to copy and paste this into some editor, and we're going to create this as an array in C. that is going to be used in VIVADO HLS as our gold reference. So basically we're jumping here to a project in VIVADO HLS which will have already our test core in place already. So we're just going to create this array here and just copy and paste the results that we copy from Matlab and edit on Notepad++, for instance. Okay, so let's explain a little bit more in the code of our core. Okay, let me just delete this to don't take your attention away. So basically simple. Okay, we have our top function gravity. By the way, we can define our top function here. Okay, so we have 3 parameters: m1, m2, and distance. Okay, so basically this code is quite simple. We are just applying here the formula. Okay, we fix our gravity to 10. Okay, so basically m1 multiplied by m2 divided by distance squared. Okay, we just add this code here to avoid the division by 0. Okay, we don't want that. We want to avoid this. We don't want to return like infinite. We want to return a bounded number. Okay, and let me put again these pragmas here. So basically the idea of this IP core is just to create these ports here. It's going to be an IP core that is going to have an AXI Lite slave interface. Okay, so M1, M2, and distance will all be part of a single AXI Lite interface called CRTLS. Okay, and also the return value of this function as well. Sorry, not the return value. When we put this return here, it's just that we are going to receive, we can detect through AXI Lite that the function terminated the execution. Okay, so basically let's save this. Let's synthesize our design. I mean, convert it from C++ code to Verilog or VHDL. Okay, and it worked. Now let's just talk a little bit now about latency. Okay, latency is the number of cycles that after you place your input in your IP core, the number of cycles that you're going to have the result. So basically here say that you're going to need 23 clock cycles to have the result. Okay, an interval just means the number of cycles that you need to wait to give a new input. Okay, think of this more or less like the throughput. Okay, but basically this is going to take 24 cycles. Okay, 24 cycles of 10 nanoseconds to put a new value. Okay, to calculate it again for some other value. Okay, here the utilization, as you see, is quite minimal. You just use 2 DSP cores, 1%. Sorry, it uses 6 DSP cores, which means this is 2% of our Z board Zynq. Okay, 1% of flip-flops and 4% of LUTs. We are not going to fight now to avoid or change this at this moment now. Okay, so here is the AXI interface. Okay, the AXI Lite interface. And let's now jump to our test core and see how we're going to test this guy here. Okay, basically we call our function here inside a loop that goes from 0 to 9, which matches exactly with the reference that we created here. So here we have actually 0 to 9 elements, 10 elements. Okay, and basically what we just do, we call our function. Okay, we calculate a difference between the result that we have now and our reference that we bring from Matlab. Okay, and then we just print some messages to say a little bit the results and stuff like that. And if the error, okay, if the difference between our gold reference and our calculated force is bigger than 1, okay, we just display a message and return a value different than 0. Okay, by the way, Xilinx recommends that you return values from 1 to 255 to indicate errors. Okay, Well, so let's just run our function. Good. As we can see, the error is quite small. Okay, here we have an error between our gold reference and our calculated function. Okay, good. Now let's, by the way, here we are simulating at the level of C or C++. We are actually just compiling and executing C code. Okay, here in code simulation, we're going actually to simulate the generated Verilog or VHDL code, okay, which can take significantly more. Okay, for instance, at my job, for instance, the simulation can take like 4 or 5 hours if you do some image processing. Okay, so let's do it. Let's choose the Vivado simulator, which is the when you chip Vivado HLS or Vivado, it's the simulator that you're going to receive. Okay, we're going to dump all the trace because later we want to see the waveform of the simulation. Okay, so let's press OK. And by the way, it's going to take a while, but it's going to simulate the C version and the here. This is the result from C. Okay, the C testing, and also is going to test the generated HDL files. Okay, I'm going to do a pause here because this can take a while. Okay. And the C simulation should be quite the same. They are. Okay. So at this stage we have an IP core. Okay. If this is going to be faster than just doing this calculation in the ARM processor of the Zynq, this is another story. We're going to see this later. But basically we are ready to go to Vivado and put our Zynq, create our block design, and run this IP core with the Zynq. Okay, so now we're going to export this RTL. Okay, and after this is done, we can switch to Vivado, to the normal Vivado, not Vivado HLS, to instantiate this IP core, instantiate a Zynq as well, and call this function. Okay, so enough of Vivado HLS now. Let's switch to Vivado. Okay, guys. So let's now in Vivado create a new project. Okay, let's call it Lab 5, I think. AXI Lite. Okay, slave. We're going to create a project for the Z board. Okay, so let's create a block design. In this block design, we're going to add our Zynq. By the way, you're going to do this, guys, so many times. It's going to be automatic in the 4th time. Okay, so let's run block automation to automatically create the ports to the DDR. Cool. Okay, now let's add our IP. By the way, okay, we put on this directory, so we come here, add repository. So lab 5 AXI Lite solution. If you put this directory, I think you'll be able to find already the core. Okay, cool. Our gravity core is there. Okay, so apply. Okay, now gravity here. Nice. Okay, now as these guys have an AXI Lite interface, if we just run connection automation, he'll do all the connection needed. And by the way, he's going also to put probably I think it will create a interconnect in between. Okay, this interconnect will allow us, for instance, actually you allow Zynq to control more than one AXI AXI4 slave core at the same time. For instance, it's like it's going to use, for instance, one master GP port that can connect any IP cores that use the AXI4 Lite interface. Okay, we have as a result an interrupt as well. When the calculation is done, we can, for instance, come here, enable an interrupt. Okay, but I think for this demo we don't need it. But just to show, is here. If you put a PL to PS interrupt port and you enable here, okay, but we don't need. Okay, so let's verify if everything's right. By the way, while he's doing this, let's remember that every AXI Lite or AXI full IP core is memory mapped. So if you come here to address editor, he's going to have an address, and for the software point of view, every parameter and the results are going to be here. Okay, so now that is saved, we come here and we create our HDL wrapper. Okay, so it's going to generate HDL code that is going to instantiate every single one of these IP cores. Okay, now is my dog trying to open the door. Just 1 second. Vem flop. Okay. Cool. So now we just generate bitstream, save, yes, and well, this can take a lot of time. Normally in my computer, the whole synthesis process take up to 20 minutes or something like this. In the future, I'm going to show some videos as well to show how to do this in a faster way. Actually, I'm learning. I don't masterize totally. The non-project way is like you create your whole project using only TCO commands, and well, let's see this in the future. So I'm going to pause and come back when it's done. Okay, so this is done. By the way, guys, if you hear some baby noise, it's my baby here who is playing around here in the lab. Okay, so let's just open the implemented design just to have a look on the course that that we generated now through VIVADO HLS. Okay. Well, just at this level, we already have our bitstream done. So we are going to, after take a look on this, we're just going to export it to Xilinx SDK, which is basically where we're going to write our code. Okay, so let's highlight our IP core gravity here. Okay, so let's just highlight with a different color. So basically, this is our IP core. All the rest is the glue logic that we have to connect it to the Zynq. Okay. Well, if you press F4 while selected, you can see the schematic of this guy. Yeah, kind of complicated, but yeah, this is what we generated. Okay, so in the project summary, we can see more or less the resources used. Okay, timing is okay, so let's just export it. So export hardware, include bitstream. Here, after this step, we're going to launch the Xilinx SDK. Okay, so this is the Xilinx SDK, which is normally where we're going to write our software that is going to run in Microblaze or Zynq. Okay, so before, let's just see here. This is our IP core that we generated. By the way, the driver is already configured, I think. So let's create file, new application project, test gravity. Okay. C++. Okay, we're going to create now a BSP based in our bitstream, in our in the cores that we have. Okay, so we create just a blank project. My daughter. Okay. Drivers, just to verify. Okay, gravity is there. By the way, guys, if the driver has not been initialized, you can come here in preference. Okay, Xilinx SDK, repositories, and you can add the repository pointing to the source directory of your solution. Basically, here in the VIVADO HLS, you have in the implementation a folder called IP drivers. Okay, gravity. So just point to this folder here, and Xilinx SDK will be able to find the drivers needed. Okay, so the IP is there. Sorry, our software is there. Okay, so here, first thing, include the X parameters. .h. Okay, also our core. Guys, I'll just stop a little bit because I will see what my daughter wants. Just 1 second. Okay. Okay, so guys, I'm back. To facilitate a little bit, there are some files that are generated if you create a C version hello world. Just hello. So, okay, hello world. That's it. Are those files here, the platform.h and .c. And also is good because help us know which other files are missing. So this guy here, we're going to copy those guys also here. Yeah, I think that's it. So maybe this guy I need to to rename it to CC, just to force the compiler to use CPP or not. Didn't work. Okay, so this file is also missing. Cool. So now we can just delete this guy and continue. Okay, so the first thing that we need to call here is init platform. Okay, now we need to initialize our core. Okay, so this is quite simple. I'll just copy and paste and explain you guys how it works. So guys, the code is quite simple. Okay, so remember that we add this header file here, gravity.h. Okay, here we have the functions that we need to use to initialize and configure our IP core. Okay, here is how we start and wait until the results are ready. Okay, here is the part that we set the parameter values or get as well, but normally you just set them. Okay, and here to get the result, by the way. Okay, so let's take a look now in the initialization code. By the way, this will be quite the same for every generated HLS core which has AXI Lite interfaces. Okay, VIVADO HLS will create a kind of driver for those guys, and the structure is always the same. The only thing that will change is it will be the name of the IP core. It will be X, name of the IP core, and the functions will be always this: lookup config, CFG initialize, and by the way, I think we don't need initialize now. Yeah, let's comment it. Okay, So basically we create a variable status, we initialize the config file using our address, okay, sorry, the device ID of our guy, okay. Then we initialize with the configuration that we just created now, and basically we are ready. Now the only one thing that I will do, I will just come here to VIVADO HLS, grab again our reference, copy here, paste here, sorry. Okay, a good idea as well is, why not, put as well your original code. I mean, EC should work anyway. Okay, we just take out the pragmas. Okay, just to take them out. Okay, we exercise our software version. Okay, by the way, you can just again copy and paste from the code that we just created. Just change a little bit. Cool. We call our gravity software mode. Okay, this part here we don't need now. Okay, and this part here is going to show the error, by the way, software mode. Okay, now let's do it on the hardware way, which means call the VIVADO HLS IP core generated. Okay. Some error. What the fuck? Ah, okay. So math. We're missing math.h. Cool. Okay. Now let's set the parameters that we need in our IP core and run it. By the way, this is going to run as well in a for loop. Don't forget, as I told you, calling AXI Lite cores in a for loop is not the best way. I mean, if you guys really need to have a stream or a burst of data that is going to send a lot of data at once to your IP core, maybe AXI Lite is not the best one. You have, as I mentioned, the AXI for stream, and using BRAMs as well. I will show BRAM in the next video. Okay, so let's continue. So let me just paste how to do it. So it's simple, guys. We use xgravity underscore set, in our case first parameter m1 to 10, m2 to 20. The distance is going to be updated inside this loop, will be from 0 to 9. Okay, and here is start the IP core execution. Okay, and then wait until it's done. So something like this. Gravity get return. No, we don't need this now. Is ready. Is done. So basically, while it's not done, we wait. Okay, and now we want to get force hardware. Get return, and basically now we get the we got our result. Okay, I will just put here let's initialize this guy, this error accumulator, to 0 as well. Calculate a difference between the gold reference and our calculated version in hardware. Okay, cool. We accumulate the error, and then in the end we divide it. So basically here now is the hardware version, we divide it by 10. Okay, so let me just put here some comments to help us. Okay, so I'll just pause now to connect my Z board and program the FPGA and run it to see if the results are fine. Okay, so guys, now I have my Z board connected, so let's program it. And after the programmation is done, we switch back to the Xilinx SDK. We probably should configure the UART in the Xilinx SDK as well, just to check. By the way, this depends on your computer, which port the UART is connected. And it's easy to know because you're going to get a message like this: process STDIO not connected to console. So basically come here, run configuration or something like this. Run configuration, yes. So STDIO connection, in my case is this port here. Okay, and well, by the way, we should take a look here because we have a small difference here, actually big difference. And well, let me check. Okay guys, the problem is actually this: the float value is not represented in memory as the integer value. Okay, so we need to have two set of functions that are going to convert a float value to its representation on memory, and from the representation on memory to a float value. So actually we need those two functions here, otherwise we are simply not able to pass the right value as a float. Okay, so as our core is expecting floats in its inputs, we need to send exactly floats. Okay, so I'll just uncomment those part here to represent, for instance, the index or those values here to a right representation with 32 bits. Okay, and to convert here from the representation of 32 bits back to float. Okay, so if we save this and run again, cool. Now you see the error in the hardware and the error in the software version are exactly the same. So guys, in the end it's become a little bit more complicated than I expected, because I simply forgot that you create a core that was using floating points, and we need to deal with the data before we send to the IP core in our C program. But it's good to learn, because on practice, you from time to time you're going to create some IP cores that he deal with floats. Okay, so just taking a look back again, the gravity function is quite simple, and how to call it from the Zynq or microblaze, which are going to do in the future, is quite simple as well. So just remember, set for the parameters and get to the return value. Okay, well guys, this closes this tutorial for today. The next video you're going to learn how to create the same thing but now using block RAMs. Okay, hope you guys enjoyed and see you guys in the next video.